Just a moment, yes. Can you see the screen?
Yes, we see the screen, yeah.
Okay, very good, very good. Okay, so let me quickly begin. So I had the fortune to experience long and fruitful collaboration with Oleg. In my talk, I will illustrate some highlights of this. And in fact, not some, very few, but I will try to let you understand some spirit of our collaboration rather than more technical result. So the first time Oleg arrived at the Volterra Center was in 1992. And he arrived just 1 month after we had completed the following paper, also missing the other 2 authors, which are, I don't know what happened, but they have been erased, which are myself, Paolo Gibilisco, and Igor Volovich. And the paper was called Young Mills Gauge Fields as Harmonic Functions for the Levi-Laplacian. Now, when Oleg arrived, I was still with my mind on the Levi-Laplacian, and therefore I started talking to him with this result obtained with Gibilisco and Volovich. And then I noticed this, for the first time, because it was the first time I was meeting him, this kind of insatiable scientific curiosity, which was one of the main characteristics of his personality, as many of the speakers of today's session have emphasized it. And he read our paper, and then we began to discuss about the notion of infinite dimensional Laplacian in general, but having in mind the particular example of the Levi-Laplacian, because at that time, and I insist that now situation has changed, it was still considered as a pathological object in analysis because of its property of being identically zero on all cylindrical functions. This property made a big challenge for infinite dimensional analysis, as remembered in this morning talk by Vladimir Bogachov. In this field of infinite dimensional analysis, Oleg was a master. And in fact, the depth of his knowledge of all aspects of infinite dimensional calculus made an enormous impression on me. And useless to say, I learned a lot of things on this first time I met. And every time I met, I always learned something new or have a new idea. Since then, I have always been convinced that Oleg was the best expert in the world in the subject of infinite dimensional analysis. So the above mentioned what we were discussing. The above mentioned property of the Levi-Laplacian, which made many people to think it was a pathological object, convinced us that this object belongs to a new level of infinite dimensional analysis. And for this new level, we coined the new term, essentially infinite dimensional analysis. Now let me go a little bit more into detail. So in the paper of this paper, I will refer HSE-NN, Accardi, Gibilisco, Volovich. The main result was the following: that a parallel transport is associated to a connection satisfying the Euclidean Yang-Mills equation if and only if, when considered as a functional defined on the space of piecewise smooth paths, the parallel transport is an harmonic function for the Levi-Laplacian. That is, satisfies the Laplace equation. I want to mention just incidentally that since '92, the most important advance in this line of research has been obtained by Boris Volkov. Who was not by chance a former student of Smolyanov. He was able to include instantons in this picture, but I have no time to discuss about also this. So what was our starting point with Oleg? The starting point was in the proof of the theorem that I have just mentioned on the equivalence of a parallel transport being harmonic for Levi-Laplacian and its generating connection satisfying Yang-Mills. the proof required to calculate the second derivative of the parallel transport along the curve, with respect to the curve along which the parallel transport goes. In this calculation, we found with Georgievich and Volovich that in addition to the Volterra and the Lévy kernels of the second derivative of the parallel transport, there is an infinite series of terms that we called singular appeared. And this infinite series correspond to higher distribution derivatives of the delta function. So since we were interested only in Young means, then we neglected this remark in the rest of the paper and concentrated on the main topic of the paper. But when Smolyanov arrived, we noticed this remainder term. So let me briefly recall that the usual definition of Laplacian of a function in infinite or finite dimension is that the Laplacian is the trace of the second derivative. In coordinates, it will have this form. So if f is a function on defined on a Hilbert space, the second derivative is an operator of the Hilbert space into itself. And in our discussion, we began, and in our discussion of the paper with Georgievich and Volovich, Oleg and I began to ask ourselves if also the singular part of the second derivative could be interpreted as some kind of traces. In some sense, and the trace give rise to Laplacian, as I will explain in a moment. So this would have given us the possibility to associate a kind of Laplacian to also to the singular part of the second derivative, not only to the Lévy part, which is the lowest singular part. So the answer to this question was the result of our first joint paper, which is called, in fact, On Laplacians and Traces. And Vladimir Bogachev mentioned this paper this morning. And I want to notice that starting from 1992 and in the following 17 years, Oleg came in the to the Volterra Center at least once every year. And I had the curiosity to count our joint papers, and they are exactly 18, which means an average of 1 paper per visit. So let me come to what we baptized with the Oleg exotic Laplacian, because at that time, really nothing was known about them, even after our first paper. It took a long time, as if I hope to arrive to the end, to understand this Laplacians. Okay, so as we said, the usual Laplacian is the trace of the second derivative. But then with Oleg, we thought that if we consider any trace on a phenomenon algebra, we can associate a Laplacian by assuming that by restricting our attention to those functions whose second derivatives are operators belonging to that von Neumann algebra. However, we soon understood that the framework of von Neumann algebra is too narrow to include several important examples which involve unbounded operators, because von Neumann algebras are algebras of bounded operator on Hilbert space. And so I will show in the following what we constructed and why we had to go beyond von Neumann algebra and to go to the domain of star algebra, which not by chance is also the standard domain of quantum probability. Okay, so we introduced in that paper the following general notion of Laplacian. We start with a Hilbert space, and we take an algebra of operators defined on a common invariant subspace of this Hilbert space. And then we suppose that on this algebra there is a trace. Remember, trace is a linear function. Well, it can be infinite sometimes, often, unfortunately it is. But the fundamental property of the trace is this, that the trace of AB is equal to the trace of BA. So what we did, we introduced the space Cn depending on H and on this not for Neumann algebra with a trace that and we call CNAH, and this is defined for every n including infinity, because we call it the Cn function, so possibly it's also smooth functions from H to R, such that the second derivative is in this algebra of operators. Okay, so for then, since on this algebra there is a trace, we can define a Laplacian, and we call it the A tau Laplacian, or simply tau Laplacian. And in fact, we simply take the standard formula, but we change the trace and we take the trace on A. And then we constructed the basic example. I mean, the example came at the end of all our study of particular case, but I tell you just the result. So, and I will give you an example immediately after. So, in fact, the main example. So let us denote A0, the algebra of compact operators on H. And from now on, H will be, well, it's not necessary to take HL2 of R, but it can be L2 of a subinterval of R. But we need for reason, we cannot increase dimension, but it is more simpler to describe in one dimension. And they note A1, the algebra of multiplication by C infinity functions on R. Okay, then you can prove, this is a theorem, that if you take the direct sum of algebra constructed in this way, A0 compact operators, then you take multiplication by C infinity function, and then C infinity derivative, that is first order differential operator, and until to n order differential operator, then is a very simple exercise to prove that this is a star algebra, and the sum is direct, of course, for obvious reasons. Then what is less trivial is that the following result. So every element of A, by definition, is written in this way. This sum is not a series because we consider the algebraic sum. So every element of the algebra capital A is a differential operator of some order, but of a finite order. Only infinity being that we allow all orders. And this means that we have that these AN are zero, almost all. So all except a finite subset. And the theorem is that if the largest, this is only true for the largest, and this explains, as you will see later, the appearance of different Laplacians. So the largest integer, such that the AN is non-zero, then this is a trace on this algebra. Okay, this was the first non-completely trivial result. Now we restrict our attention to functions which have an integral kernel. So, therefore, I will show to you that this abstract definition we gave, in fact, is a nice analytical interpretation, because the usual Laplacian corresponds to the case is when the second derivative is trace class, hence it is compact, and therefore it is in A0, in the zero order algebra. The Lévy-Laplacian corresponds to the case in which the second derivative is trace class plus a multiplication operator. And the exotic Laplacian correspond to integral kernels in which we have higher degrees of singularity. I will be more specific in a moment to say what does it mean higher degree of singularity. Okay, so let us be more explicit. Let us fix the Hilbert space to be L2 of 0, 1, and the variation space. So we take derivatives along this subspace which is the space of C-infinity functions with compact support in the open interval. This is very important for what follows. Okay, now we restrict ourselves to functions who have second Frechet derivative, and obviously, by definition, this is a symmetric derivative, is a symmetric operator, and we want that HV is in the domain. And the most important property, and now you begin to recognize what was our motivation, is that when we take the matrix element of the second derivative, since we are assuming there is integral kernel, we have a first kernel called the Volterra kernel, a second kernel, the Lévy kernel, and then we have what we called with Oleg, well, these are the terms that we had found empirically with Gibilisko and Volovich. But now we call them the singular term. And this HN here, you see, the Lévy term correspond to the function itself, and the singular terms correspond to the higher order derivatives of the function. Okay. Now we assume that the kernel is boot also. We put a lot of assumption because we were interested in the general structure. And I want to emphasize that very little has been done to put more realistic assumptions since that paper. So the third term was the one, as I already said, suggested by the paper, by this paper that on the Yang-Mills equation. Corresponding to this function, we obtain different classes of Lévy-Laplacian, because we have the integral operator corresponding to the Volterra part is a trace class, in this compact, and therefore the trace is the usual trace. Now, what is the trace in this case? Well, it is for this operator, we can also introduce the multiplication operator by the kernel itself. They are all kernel with the kernel on the diagonal, so there is only one variable here. Okay, so what we can prove with Oleg is that the trace that Paul Lévy had introduced is equivalent to our trace AN for n equal 1. And is equivalent, and the trace 0 on the compact is the usual trace on the compact operator. Okay, so, but the new result was that the Lévy trace was our trace for n equal to 1. What happens for greater n? For greater n, we, using standard integration by part, essentially, we simply write the kernel in this way. And so you understand in what sense we speak of higher singularity of the kernel. Okay, so this we proved that now the problem remains to understand what is to relate this trace in some sense to second derivatives, because if we want a Laplacian, second derivatives must be involved. Okay, so I already said the Volterra kernel part of the kernel gives the standard trace, which means the Volterra Laplacian. Then the second, the second order, for the second order derivative, we have that the standard Laplacian as the form in terms of second order derivative. Now, the Lévy Laplacian, as introduced by Paul Lévy, was defined as the limit of the Cesaro means of the second derivative, not of the second derivative itself. And we proved that delta L F, the Lévy Laplacian on F, is exactly our first trace, tau1. So the trace corresponds to differential operators of first order. Now, Paul Lévy also gave another characterization well, this was the same as I mentioned before, so I don't. So now what happens for what essentially Paul Lévy proved is that this limit of the second derivative is equal to the limit that you can, is equal to the integral. I mean, this identity, remember that tau1 is the integral of the singular part, that is of the multiplication operator corresponding to the density, to the kernel of the second derivative. This was the Levy theorem, because it's non-trivial to prove that this integral is equal to this limit. In fact, this is not true for all bases, but for some very special bases, which are called by Paul Levy equally dense and uniformly bounded. So what we proved in the paper with Smolyanov was the following. Let us now take the singular part of the second derivative of a function f. Then what we have is that the limit of the Cesaro mean of order 2r plus 1 is up to a multiplicative constant, the Levy-Laplacian associated to the trace of order 2r plus 1, which means, as I have already said, just the integral of the kernel, the diagonal kernel, because by assumption, the R kernel is a multiplication operator. Okay, so this was another result of that paper. Another result of that paper was that we gave the first explicit solution. There were other existence theorems, but no explicit solution. And we had it with a special trick on which I will not have time to enter, but maybe for you who are interested in semigroup, it may be of some interest to enter in this part. Okay, but we found this solution of, and it was a semigroup, and we call it the Levy heat semigroup. However, we were not able to deal with the exotic Laplacians, you see. And so we, in this paper on 93, we posed the problem: how do the heat semigroup for exotic Laplacian look like? And this took, to answer this question, it took a lot of years, because the answer was found many years later in this paper that I mentioned of 2013, published in IDA-QP. But the important point is that in order to arrive to this result, the crucial step was another result that we obtained with Oleg, namely a generalization and higher order, not a generalization of Cesaro mean, a theorem which connects Cesaro means of different orders. There was a huge literature of Cesaro means of any order, but this theorem was not there. So the theorem is this: if we have a sequence of numbers, we call CPA the Cesaro mean of this sequence of order P. What we proved with Oleg is that if the Cesaro mean of order P for the sequence A exists, then the sequence Cesaro mean for the sequence not A, in fact, this is a misprint here, sorry, the not A, but K times A also exists. And there is a, sorry, there are two misprints. This is the Cesaro mean of order, let me correct. Okay, so the theorem was, if the Cesaro mean of A of order P exists, the Cesaro mean of order P plus 1 of K times A, that is this Cesaro mean of order P plus 1, not only exists, but is equal to P over P plus 1 times times the original Cesaro mean. Sorry, I was a little bit in a hurry, because I had a short time to prepare this talk. And, well, okay. Okay. So this was the result, you see. But a very interesting thing is that we had the converse of this result, namely that if the Cesaro mean of order P plus 1 exists and is equal to Cp plus 1, then if we take AK again now, error, again, misprint, forgotten. Okay. So if we take the Cesaro mean of order P of AK divided by K, then not only it exists, but is equal to what you expect from this formula. But of course, this formula, you can always apply this formula, but this will not guarantee the existence of this limit. Okay. So now I think this is a good time to stop, because I want to maybe leave time if there are some questions. But if you prefer, I can continue and show you how it was the explicit solution of the Levy heat equation.
How much time do we need for further presentation?
I say 5 minutes.
Yeah, I guess we can survive with 5 minutes. I mean,
So
this is the last talk. There is an advantage.
Yes,
no lower boundary.
I have an advantage. I will use this. Okay, thank you for giving me the opportunity to use this advantage. So I will be quick and not abuse of your time. So the standard Laplacian, and you know the standard heat equation. Okay, now, but let us take the heat equation with the coefficients, depends on the dimension and goes to 0. Then the Levy-Laplacian is defined in this. So you can obtain intuitively Levy-Laplacian as a limit of diffusions with decreasing diffusion coefficient. Okay. Now, okay, we use the note. This is something that I think is very interesting, because it's a physical interpretation of the Levy-Laplacian. Because if you write square of the second derivative, the square of momentum in quantum mechanics, then it is the free kinetic energy. So the Levy-Laplacian means that a quantum field theory based on Levy-Laplacian will be a quantum field theory in which not the kinetic energy is finite in finite volume, but the density of the kinetic energy is finite in finite volume. So this will be interesting, for example, for solid state physics of description of very condensed matter. This kind of Laplacians can be really have a physical meaning. Now we want to, our idea was to go to a Lebesgue free approach to the heat equation. So the standard heat equation on function is solved, and everybody knows how to solve it by going to Fourier transform. Okay. If you go to Fourier transform, then you invert Fourier transform and you get the solution of the heat equation. But the correspondence of the given by Fourier transform function in function, it requires a privileged Lebesgue measure if you do Fourier transform with Lebesgue measure. And Oleg taught to me that the really intrinsic correspondence is not between function and function, but measures and function, because this correspondence has inverse theorem given by Kolmogorov, Sazonov, Millos, Gross type theorems. Okay, so we interpreted the heat equation as an equation of measure. So you see, instead of, if you multiply formally the standard heat equation by decay, you obtain an heat equation on measures, which is this one. The measure you replace CK decay by psi decay, which is a measure. Okay, so this is our trick that we use. And on measures, Fourier transform has a meaning. So we can go to momentum representation. But in momentum representation now, we can use the approximate solution of this. And now I tell you just the main idea. Imagine that so that we are looking, well, we have to do some technicality because to speak of ergodic measures, we have to have some shift, some dynamics, which gives ergodicity. And we took the shift along a given, as a dynamics, we took the shift, we took a representation, we took the measure, well, let me say, at least the symbols. We took the standard, a standard triple, in which E has both function and H is a Hilbert space. and we considered measures on the dual of the test function space. Okay, and we consider an orthonormal basis in the test function space. Then we have the random variable. We can consider for every measure on a star, we have a random variable, which is well known, the projection on the basis. And therefore, if we take the solution up to time n of the heat equation, we have an explicit formula. But now suppose that this is the variance of the random variable. The k square is the variance of the random variable for a given measure, for the given measure. Let me write this. So we can define the stationarity of the measure. We have the family of random variable, which is this. We have a measure, and we consider measures which are stationary and which have finite second moments. This means M2. M2 means, and the EJ means that the measures are stationary. And now we can solve easily the heat equation for a measure, the initial value, the measure psi 0. And now this was our remark, our trick. If psi 0 is ergodic, we can apply the ergodic theorem, because this sum here is nothing but the sum of the square of the random variables, which are independent in our assumption, which are stationary. And so by the ergodic theorem, the limit exists. And so we have that the explicit solution of the heat equation for the Lévy-Laplacian was exactly given by the what you expect, the limit of this expression here, the limit of this expression here. Now we know this, the limit will be in general a random variable, not because the expectation may not be trivial. It is trivial only in the ergodic case. And what are the ergodic measures for the shift in that basis? They are precisely the eigenvectors of the Lévy-Laplacian. You see, let me state precisely the theorem. The Lévy-Laplacian in momentum space is this, and the explicit solution is the expectation value on the algebra at infinity for the ergodic family of measures, a stationary family of random variable phi. And the final theorem is, and the initial, if the initial measure is an eigenvector of delta the Lévy-Laplacian, if and only if it is ergodic, and the eigenvalue is precisely its variance. So just to see that this paper, it contains a lot of ideas. Then we went on to develop the connection with white noise, etc. In a lot of papers. We studied the change of variables, but you see a deeper study. Then with Vladimir Bogachev, we extended this to the Ornstein-Uhlenbeck process, and we also with Vladimir Bogachev to apply the technique of Dirichlet form. And there are many, even for the Ornstein-Uhlenbeck, there is some problem that still remains after so many years. And this with Vladimir, we proved that the second order part must be taken as Lévy, but the drift part of the stochastic equation must be taken as usual series. So we cannot understand why, passing from Brownian motion to Ornstein-Uhlenbeck, this in the exotic Laplacian, this difference arises. So you see, there are a lot of things to be understood in this field. And this is what we called with Oleg the field of essentially infinite dimensional analysis. Thank you very much.
Thank you very much, Luigi, for your interesting talk. So let us thank the speaker. And other questions?
Recording stopped.
So other questions to Luigi?